Hi, in this video, we are going to go over structural and conformational isomers of alkanes. So structural isomers or constitutional isomers are compounds with the same molecular formula, but different atom connectivity, so how the atoms are bonded together. They are different compounds and have different physical and chemical properties. So you can see here, structural isomers, we have butane and 2-methylpropane. In butane, we have C4, hydrogen is 3, 6, plus 4 is H10. 2-methylpropane is 1, 2, 3, 4, C4H 3, 6, 9, 10. H10, they have the same molecular formula, but they're bonded different ways. Butane is a straight chain, and 2-methylpropane has a branch in the middle. They have different physical and chemical properties. The boiling point of butane is negative 0.5 degrees Celsius, and the boiling point of 2-methylpropane is negative 11.6 degrees Celsius. These two molecules are the same molecule and they're called conformational isomers. So there's a difference between conformational isomers and structural or constitutional isomers. So conformational isomers are the same molecule just with a rotation of a bond. So this is a 4-carbon chain, all single bonded together. Over here, it's 4 chain, but this 4th carbon is just rotated downwards. It's not a branch to another carbon. It's still bonded to this 3rd carbon. It's just rotated down. To convert one structural isomer to another requires breaking 2 or more bonds and reforming 2 or more bonds. Converting one conformational isomer to another requires only rotating about 1 or more carbon-carbon single bonds. So you would just have to rotate around this bond to get back to this molecule. They are the same molecules and therefore have the same physical and chemical properties. So identifying structural isomers, remember they have to have the same molecular formula and they just have different shapes. So this is the same example as before. So the possibilities include many conformations and many different Lewis structures. So this is the most common representation of an alkane is just a straight chain. This is a 5-carbon straight chain alkane, and these are all the different structural isomers of it. You can see each one you have a different branch, okay? Or these are many different conformations of them, not structural isomers. These are conformational isomers. You can see that they just all are on the straight, all along the chain. There's no difference in bonding. They're just moving or rotating around a single bond. Structural isomers, the number of structural isomers that exist for any given molecular formula increases with the number of carbon atoms. So if you have 4 carbons, there are 2 different structural isomers. If you have 5 carbons, there are 3 possible isomers. If you have 6, there's 5, and so on and so on. If you get up to 10, there are 75 different isomers. So as you increase the number of carbons, you increase the number of structural isomers possible. Structural isomer properties. Straight chain isomers have higher boiling points than branched isomers due to the difference in surface area and therefore dispersion forces and molecular dispersion forces. So you see that pentane is a straight chain alkane. 2-methylbutane has this branch off of it, and then 2,2-dimethylpropane has 2 branches off of the same carbon. These two have larger surface areas. They're bigger, right? They have a bigger surface area than the straight chain, and it's easier to break those bonds. And therefore, it has a lower boiling point because it's easier to break those bonds than the straight chain. So for practice, determine which pairs are structural isomers. So the first thing you have to do when you determine if pairs are structural isomers or if they have the same formula So you want to see if they have the same chemical formula and then see if they have the same bond connectivity. So go ahead and pause the video, work on this, and then when you're ready, come back and we'll work on it together. Okay, so this first one, what we're going to do is we are going to look and we are going to see we have 1, 2, 3, 4. We have C4. We have, let's count how many hydrogens. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. Over here, we have 1, 2, 3, 4, 4 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 H10. They are the same molecular formula. Now we want to know if they are structural isomers or conformational isomers. So we see here that we can follow it all in one chain, and we can follow this all in one chain. So therefore, it is just rotated along one bond. So they are conformational, not structural. So this one, we're going to count the number of carbons and hydrogens in each. We have 1, 2, 3, 4, 5. C5, how many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. H12. We'll count the carbons here. 1, 2, 3, 4, 5, 6. H 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. They don't have the same molecular formula, so they're not same or isomers. They're not isomers of each other. They're completely different. So let's do C. We have 1, 2, 3, 4, 5, 6 carbons. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens. And let's do this other one. We have 1, 2, 3, 4, 5, 6 carbons. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens. They have the same molecular formula. So now we want to see if they have the same connectivity. We have a branch on here on carbon 1, 2, 3 of a 5 carbon chain. So branch on 3. On here, we have a branch on 2. They are bonded differently. The carbons are, the CH3s are bonded on 2 versus 3. So this is a structural isomer. So in summary, alkanes freely rotate around their carbon-carbon single bond, and the various rotational forms of a molecule are known as conformations, or conformational isomers. Structural isomers, though, are different than conformational isomers. Structural isomers have same molecular formula, but different connectivity of atoms. They're bonded differently, and therefore have different physical properties. Due to fewer dispersion forces, structural isomers' boiling points decrease as the surface area of the molecule decreases in more highly branched isomers. So the more branching you have in structural isomers, the lower your boiling point is going to be.